All right, so the next type of application problem is uniform motion. So uniform motion is talking about, you know, things that are in motion. So relationships between the rate at which you are traveling r and the time at which you travel t. You can find the distance d traveled by the formula distance equals rate times time. So this is going to be an important part of the relationships that we're going to be using when we set these problems up. So distance equals rate times time. I'll write that a little bigger. That's a relationship, again, with uniform motion problems. All right, so let's look at this problem here. It says, and this is exercise problem 2. It says, Jimmy leaves Crosby driving towards Big Lake, averaging 66 miles per hour. At the same time, Bruce leaves Big Lake, traveling towards Crosby, averaging 60 miles per hour. How long will it take them to meet if the two cities are 105 miles apart? So this should be 105. And what I did, just so I understood the question, and again, this is our first part, understand the question. What I did is I sketched the situation. So in Crosby, Jimmy's leaving and he's heading towards Big Lake. And then Bruce at the same time is leaving Big Lake and heading towards Crosby. They're going to meet somewhere, but they can't meet right in the middle because Jimmy's going a lot faster than Bruce is, or averaging a faster speed. But I do know that the distance between Big Lake and Crosby is 105 miles. So when I do this, I'm understanding the situation. That's what the sketch is for. But the other part of part 1 is we want to organize all information and quantities for both, or for Jimmy and Bruce. And this is where I like to use a chart. So I'm just going to construct the chart here. And there's going to be two columns, one for Jimmy, or 2 rows, sorry, and one for Bruce. These are the two people, in this case, in motion. But then for each one of these, I want to define the rate, the time, and the distance for each one. So this chart is going to help me keep my information organized. So like in this first column, or this first box, this would be reserved for Jimmy's rate. And then the bottom, this would be Bruce's rate. So when we organize, this is all step 1. I want you to kind of look at what we've created. We created a sketch of the situation, and then we know that Bruce and Jimmy are the two components that are in motion here. I want to use a chart like this to keep track of all their information. So let's start with the rate, R. So I'm given, we're going to start filling in this chart with given information. So the given information is the rates. I know that Jimmy is averaging 66 miles per hour and Bruce is averaging 60 miles per hour. So I'm just going to put these rates in here. So the next part of this, I'm going to ask myself, what am I looking for? And that's kind of the start of my definitions, right? The quantities. And it says, how long will it take them to meet? And when it asks for how long will it take them to meet, that's talking about time. So I know I want to define the time Jimmy drove and the time Bruce drove. So how are these related? So look for the relationship about their times. So you notice it says at the same time Bruce leaves Big Lake. So that means Jimmy is on the road for T hours, we'll just use T, and Bruce is on the road for the same amount of time, T. So they left at the same time. So in this case, these variables both represent Jimmy's time and Bruce's time. Now this is the important part here, step 3. And step 3, we're going to use, and again, it's our last column, it's distance. We're going to use distance equals rate times time to define our expressions for their distances. Now, Jimmy can't drive 105 miles, right? Because 105 miles is the total distance traveled. Jimmy, if I look back up here, is only traveling part of that distance, and Bruce is traveling the other part. So we'll worry about that in a second. When we do this, we know that if I take rate and I multiply by the time, I get distance. So if Jimmy's rate is 66 and his time is T, the distance we could write as 66 times T, or 66T. So I'm using that relationship between rate, time, and distance to define an expression for the distance. So Bruce, his average rate is 60, the time is T, so the distance could be expressed as 60T. Now, where does our equation come from? So I've got all the information I need for each person. I got everything defined for my expressions for rate, time, and distance. So step 4, or the 4th step, yep, is we're going to take, and we now need to relate both distances. Is there something we know about both distances traveled? So one of the things that I know about their distances is that the two cities are 105 miles apart. So if I total the distances, if I add their distances, I should get 105 miles. So I'm just going to use the expressions that we defined. The distance that Jimmy traveled would be 66T, plus the distance that Bruce traveled would be 60T. If I add those two together, I should get 105. So it kind of goes in order, and again, we'll do another problem, but organizing the information and how do we construct the problem solving, right? And where does this equation come from? So I'm using those expressions for distance, and I'm understanding for this application, the total distance of the two would add up to 105. So let's go ahead and solve this. So I'm going to add my terms together. This would be 126 T equals 105. And then I need to divide by 126 or cancel, right? And so when I do this, I get T equals, and this would be a tough one to simplify, but 21 actually goes into 105. This would be 5 times 21, and this is 6 times 21. So again, that would be harder to see. The 21s cancel. This is 5, 6. So the answer to our problem then, T is 5, 6. Well, this is in terms of hours. So we have to be careful a little bit here. So this would be 5/6 hours. So how long does it take them to meet? 5/6 hours. Well, 5/6 hours, right, is the same as what or how many minutes? So hours is 60 minutes, right? So if I take 5/6 and multiply by 60 minutes, right, 1 hour is the same as 60 minutes. So if I multiply these, then the 6 cancels with the 10 leaving, or 6 cancels with the 60 leaving a 10. So this would be the same as 50 minutes. So that's a conversion that we could use, knowing that there's 60 minutes in an hour. All right, so you could review that, go back through and listen to that again. But the big thing is, how do we come up with this equation? How do we keep all the information together? So let's try this next one. This is another type of uniform motion problem, number 7 here. And the first thing I'm going to do is just understand the question. It says a plane leaves Atlanta heading towards San Francisco at 9 a.m., traveling at 400 miles per hour. Another plane leaves Atlanta heading to San Francisco at 10 a.m. the same day, traveling 550 miles per hour. What time will the second plane catch up with the first? So we got 2 planes, and again, I'm just going to sketch this. We got one plane. These are planes. Sorry, they're terrible looking planes, but they're leaving Atlanta. One plane leaves Atlanta and starts heading towards San Francisco. And then a second plane, supposed to be a plane, leaves Atlanta an hour later, traveling to San Francisco, right? On the same route. So if you think about it, we want to know when they catch up. So we want to know somewhere in between. The second plane is going faster, so it's eventually going to catch up to the first. So we know we have to organize the information for both planes. So I'm going to make a chart with rate, time, and distance for the first plane. And that plane left at 9 a.m., right? I'll just put that up here too. And the second plane, started at 10 a.m. And I want to organize this information. So the first thing I'm going to start with is the rates. That's given to me. So let's just write the rates in. The first plane was 400 miles per hour, and the second plane was 550 miles per hour. So now we want to define the times. And you notice that the times can't be T and T like they were last time, because these planes, the first plane left at 9 a.m. and the second plane left at 10 a.m. So that means the first plane is actually in the air an hour before the second plane even starts. So how are they related to each other? So if the second plane is T, right? Or if the first plane is T, then we can define the second plane as being in the air an hour less, because it started an hour later. We could do T minus 1 here. Does that make sense? So the first plane, if it started at 9, that would be the time the plane is in the air, the first plane. But since the second plane left at 10, we need to define the time as T minus 1. It's an hour less. But the third step now is basically done for us. We're using that distance equals rate times time. Whatever we have for the rate, we're going to multiply and get an expression for distance. So the first plane would be 400 times T, and the second plane would be 550 times T minus 1. So we're just, again, the last column, that distance column, we're creating these expressions. And now we're going to take these expressions and we're going to think about step 4, How are their distances related? And if we think about what we're after here, we go back to our diagram and we think, well, I eventually want to know when they catch up. So this represents the distance of the first plane from here to here. And then the second plane, the distance would be from here to here. So eventually the second plane will catch up. How can I relate the two distances? Well, when they catch up, they're going to be exactly at the same distance. So in this case, when that one catches up, I know that the distances are the same. So my relationship is that they're equal. And I'll just take the two expressions, 400 t equals 550 times t minus 1. Okay, so once I have my expressions for the distances, how are they related? Well, I know this one is a catch-up kite problem, so the distances eventually will be the same. Okay, so let's start solving this. We have 400 t equals, and we'll distribute. So we have 550 t, and then 550 times negative 1 is negative 550. So if I move the t terms to the left side, I end up with negative 150 t equals negative 550. And then dividing by negative 150, I get t equals it looks like if we can cancel the zeros, we'd get 11 over 3. So 11 over 3 is the same as 3 2/3 hours. Now we have to be careful. What this represents when we answer our question is that the actual answer. So 3 2/3 hours. Well, 2/3 hours, we could change to minutes. So 2/3 times 60 minutes. The 3 cancels with the 60, leaving a 20. This would be 40 minutes. So we could get t equaling 3 hours and 40 minutes. But again, the question is, what time will the second plane catch up to the first? So that's when we need to go back. If t represents the time of the first plane, right? T represents the time of the first plane. Then this is from 9 a.m., how long the plane's been in the air. So we'll start at 9 a.m. and we'll add 3 hours and 40 minutes. So that means the time would be 12:40 p.m. So they're going to meet at 12:40 p.m. So I hope these uniform motion problems, if you look at them completed, they look terrible. But remember, we're going through a process. We're constructing our expressions. We're using diagrams, things like this. We're coming up with an equation. And then when we're done, we're just being careful with how we answer the question. Make sure we answer the question with what was asked. Okay.